Hi, we're going to talk about how to remove a node from a tree in this video. So node removal is the reverse of insertion. So it's a very essential and common operation in a tree. Now to do a bit of quick review, in a linked list, when we want to remove a given node, what we do is we set the previous node's next pointer to skip the current node and just point to the next node of the current node. So we will do something very similar when we remove a node from a tree. Now, as far as the previous node is concerned, we have to consider two different cases because a node's previous node can be a sibling and it also can be its parent, and we will have to handle those two cases slightly differently. Now, there is actually a third case where the previous node doesn't exist, and that would be the root. And we are going to do a bit of hand waving for now on that particular case. And at the end, though, I'm going to ask you to try to handle that case. Another very important thing to know, at least in our implementation of the general tree, is that when we remove a node, the whole subtree that is rooted in that node is considered removed. So in this example, if the node we're removing is node B, then after it's done, then the whole subtree that starts at B is removed from the tree. So what's left over in the tree would be the node A and C and potentially other things. But again, the whole subtree that starts at B is gone. Now I have implemented the remove node in the FhTree class. It's not that many lines, but I'll go through it line by line to make sure we understand what each line does. So the overall idea of removing a node is that we'll go back to its previous node and change its next pointer to point to the node after the node we are trying to remove. Now the previous pointer, in case of a tree node, can point to either a parent or a sibling. So the first thing we have to figure out is how do we tell whether it's pointing to a parent or a sibling? Well, we can do that by checking. So in this case, let's say we're trying to remove C, and C, the previous pointer it's pointing to a sibling. We can tell by looking at the picture. Now, in terms of the code, the way to do that is that we'll check the node's previous sibling is pointing to the node that we're trying to remove. If that is true, which is so in this case, then we know the previous node is a sibling of the current node that's being removed. So in that case, then the pointer we'll try to change would be the node's previous sibling would now skip over the node we're trying to remove and point to the sibling of the current node that's being removed. Okay. And then the next thing that we'll do is after we change this forward pointer, we have to change the backward pointer, right? So the backward pointer, for the backward or the previous pointer of the next node, then it doesn't really matter if it is the parent or the sibling, because we always call it the previous pointer, right? So that previous pointer, the sibling's previous pointer, can then always point to whatever the current node's previous pointer is pointing to, whether it's a sibling or a parent. Now let's look at a case where we're trying to remove a node and its previous pointer is pointing to a parent. So node B here, the previous pointer is pointing to node A, which is the parent of B, right? So when we do this check, then node B previous sibling, well, in this case, it's the root node, so the sibling here is none. So none is definitely not node B itself. So this is going to be false. And when this is false, we know that the previous node is a parent, and therefore the quote unquote next pointer we're going to have to change in the parent would be the first child, which used to point to node B here, but we're trying to remove node B, so it should now be pointing to the sibling of node B, which is C. Now we have to adjust the backward pointer in C, and that, as we said before, it's the previous pointer used to point to the node that is currently being removed, and now it should point to the previous node of the node that is being removed, which is, in this case, is A. So again, the same code, at least this line of code would work whether the previous node is a parent or a sibling. Now, I probably didn't mention this about this check. If node.zip, we want to make sure that it is not none in case, let's say, we're trying to remove B and it has no sibling, right? So in that case, we don't need to adjust the previous pointer of its sibling. Now, next, I'm actually going to skip the size for now because that, believe it or not, it's a little more complicated. So I'm just going to skip to this last line that here it says just zeroing out a bunch of references. That's because, we want to remove this node from the tree, but now this node is still pointing to some nodes in the tree. Well, we should set all of those references to none. So that includes the 3 references, the node's previous first child and the sibling, as well as the root, because, well, it's this node we are removing from the tree, so its root should no longer be pointing to the root of the tree that it's being removed from. So all of these are set to none. Now let's go back to look at what we should do with the size attribute of the tree. So we just removed one node from the tree, so we decrement the size by 1, correct? Well, let's look at the result. So we're removing the node, just removing a node B, and we'll print out a tree after we're done. So if we run this, and this is the original tree, and now after removing B, this is the tree. And it looks good that we actually, the subtree that starts at B, this whole subtree here, is no longer in the tree, right? So we actually got that part right. But do you notice anything that's still not quite right with this tree? Well, look at the size here. The size is 13, but that's obviously not right. We do not have 13 nodes in the tree after the whole subtree at B has been removed. So what was the problem? So the problem is that even though in our implementation of the general tree, we considered the entire subtree that is rooted in a node that's removed is gone, but when we're decrementing the size of the tree, we're only decrementing one node rather than the size of the entire subtree. So how do we solve this problem? Well, it's actually a little fun problem to think about, so you're welcome to pause the video and think through it yourself first. I'm going to tell you now that it's actually not a very straightforward problem. The reason for that is the size of the subtree that is rooted at a particular node. Well, it can be 0 or it can be 1,000,000. At the node level, there's no information about the size of the subtree. So in order to actually decrement the tree size by the right number, we actually have to go through all of its children and children's children and so on, and remove every single one of those nodes. And as we remove one node, we decrement the size by 1. So that sounds like a lot of work just to calculate the size correctly, but that's probably also the simplest way to do that. Now, so we are in remove node, and now we have to visit all of its offspring nodes and remove every single one of them. Well, that sounds like we are going to have to call remove node inside remove node. So we're going to make remove node into a recursive function. Well, I did say the tree implementation loves to use recursion, right? So here is another use of it. Now, that's the idea. If you want to try to write this code yourself first. Again, feel free to pause the video and give it a try. So here is where I would write the code. So at the beginning of remove node, if the node has a child, then we'll remove the child. Right? Now, you might wonder why I do this before removing the node itself. Well, the practical reason is that at the end of removing the node, we zero out all the references in that node. So we're going to lose node first child. So we should do that before we lose the that pointer, right? And also, it really, if you think about it, it kind of makes sense to remove everything below this node and then remove the node itself. So that's why the recursive call is the first thing that we do in this method. Now, I've already typed it out here. Let's see if it works. So we'll run this, and now the size of the tree is no longer 13, but it's 11. It still doesn't seem right because there are 1, 2, 3, 4, 5, 6 nodes here, not 11. What happened? Well, when we run into some unexpected problems like this, it helps to print out more information. So what we can do in this case is that we can print out the node that we're trying to remove. That's one message. And then when we are done, when we actually remove the node itself, we also say now that the node is actually removed. And then let's look at what actually happened. So we run this, and here are the bunch of debug messages that we see. Now, if we look at the nodes that are being removed, it's B, E, and L. And let's look at where they are in the tree. Well, we're trying to remove node B, and we try to remove its first child, E, and E also has a first child of L, right? So yes, we are only removing 3 nodes. So those are the nodes that's shown here that are being removed. And also, I'd like to draw your attention to the fact that this is the order that the nodes are requested to be removed. However, the nodes that when they're actually removed is in the reversed order. So the L node, the node at the bottom, is removed before E, is actually removed before E, which is actually removed before B. So B was the first one that we want to remove, but it's the last one that is actually removed. And that actually makes perfect sense if you think about the recursive call that actually happens at the beginning of the remove call. Again, the thing we just talked about is that when we want to remove B, we actually remove its child first, which is E, and then before we remove E, it actually removes its child first, L. And then when all those are done, E and L are removed, then we come back and remove B. So that kind of give you a better insight or better understanding of how this remove works. Now, still, that doesn't help us because we are trying to remove the entire subtree rather than just the first children reachable from the node that's being removed, right? So again, how do we fix that? And if you'd like to challenge yourself, pause the video, think about it. It is a single line change. So to fix the problem, we have to understand what caused it in the first place. In this case, the problem is that, let's say we're removing node B, right? And we are done with the recursive call. Now, what the recursive call did was that it removed the first child, the original first child of B, which is E, and also the original first child of E, which is L. However, after E has been removed as the first child from B, the B still has a first child, and that is the sibling of E, right? So B is still has first child, and the subtree that is reachable from its new first child. So that's why the size is not decremented properly. And the fix then would be very simple, right? That as long as there is a first child, we should just keep removing it. Don't stop at the first child. So to fix that, we will just say, instead of an if, we do it with a while. So, and if we run that, now we have a size of 6, and there are 6 nodes in the tree. So we've finally solved the problem. So here is a little exercise for you that I actually would like you to re-enable these 2 debug messages that prints out when we request to remove a node and when the node is actually removed, and actually look at the output from there when we remove the node B, as we did previously, and that examine the output to look at the order in which the nodes are removed, and make sure that you understand why they are removed in the order that they are, and hopefully that will help you to really understand how remove node works and how the recursion works. Because if you think about it, because we're doing the recursive call in a while loop, potentially we could be making, let's say, 100 or even 1,000 recursive calls, and each one of those recursive calls can also make another 100 or 1,000 recursive calls. So this recursive call here really kind of becomes fairly interesting and fairly intricate. So feel free to bring up questions and discuss it in the discussion forum. Now, the next thing I would like you to try is that, as I told you at the beginning, there are actually a third case in the remove node, and that is removing the root node of the tree. You can try to see what happens now when you just run the code as is to remove the node of the tree. And if there is a problem, I would like you to handle it by just special casing it, right, and do the right thing. So please give that a try as well.